Hi everyone. So last time I introduced how the continuous time Markov chain works, just briefly, right? And so today I'm going to give you some good exercise problem. But before we do that, I want to refresh your memory. Okay. Hold on a second, please. Did I? So I gave you the exercise problem, right? Okay. Just to make sure. Okay, so last time I introduced continuous time Markov chain, and we talked about unlike the discrete time Markov chain, the continuous time Markov chain, each value of t, that is the transit points, random points in time, right? But just like the discrete time Markov chain, continuous time Markov chain also has the memoryless property, right? So for any given past state and the present state, the conditional distribution of the future state is always independent of the past state, but depends only on the present state. Okay? And the discrete time Markov chain changes states only at discrete points in time, whereas the continuous time Markov chain may change its state at any point in time, right? So I mentioned that transit points in the continuous time Markov chains are not necessarily integer, okay? So here the t sub I is the length of time that we spend in a state before the transition occurs, okay? And this t sub I always follows the exponential distribution. That's our assumption. So we may say that the continuous time Markov chain is a stochastic process that moves from state to state in accordance with a Markov chain, but the length of time spent in a state before making a transition into other state has the exponential distribution. Okay? And last time we also learned that from these two equations, we have come up with this relationship. So here lambda sub ij is the transition rate from state I to state j, right? That's what we talked about last time. And we also talked about how to build the matrix lambda that represents the transition rate for each state. So for the matrix lambda, of the diagonal elements, we typed in transition rates from state I to j. And on the diagonal, we typed in the transition rates from state j to all other states. And we put negative sign to distinguish from all the other transition rates. Okay? And we use this matrix for balance equations, right? And for a continuous time Markov chain, the steady state distribution is computed by solving this system of equations. But this linear system of equation is also linearly dependent, so keep in mind that one of the equation has to be removed. So just arbitrarily choose one and then remove it, okay? So instead of using this balance equation, we can use pi times lambda equals 0. Okay, so that is the alternative way for you to determine the steady state distribution for the continuous time Markov chain. Okay, also last time we talked about the birth-death process as a special case of continuous time Markov chain, right? So birth-death process models the size of a population. In the birth-death process, the population always increased by 1 and also decreased by 1. In the birth-death process, another assumption is that the birth and death are always independent of each other. Okay? And for the birth-death process, steady state distribution would be determined by solving these two equations. So these two equations are, I'd say, a streamlined version of the formula. Okay? So keep in mind that this formula works only for the birth-death process. It doesn't work for any other types of continuous time Markov chain. Okay? Okay, so now let's consider one very simple example. I believe this example is very similar to the one that we talked about last time, the light bulb example problem. So let me give you a couple of minutes. Why don't you try to build up a continuous time Markov chain model, okay? And then try to answer for the question. So it asks you the fraction of the time that the system will fail, okay? So obviously we need to determine the steady state probability distribution first, okay? Okay, so let's read the problem description together. An airline reservation system has two computers, one online and another standby. When the operating computer fails, after an exponentially distributed duration having mean time t sub f. And then the failed computer is replaced by the standby computer, right? And there is only one repair facility, and the repair times are exponentially distributed with mean time of t sub r. So we'd like to determine the fraction of time that the system will fail. So in that case, fraction of time that both computers are failed, okay, actually. So we're going to do that. But beforehand, we need to build up the Markov chain model, right? So, okay. So how do you define the state of system in this case? So if I say each state represents the number of computers, maybe in good condition, then let's say so we have state 0, okay. So in this state, both computers working, right? No, both computers have failed, right? So both computers failed. And also state 1, one computer has failed, right? And the other one is in good condition. And then here, both in good condition, right? So here we have a transition. So what would be this transition rate? I would say that is the service rate or repair rate, right? So what is the repair rate? 1 over TR, right? Okay. 1 over TR. In other words, this rate will be the failure rate, right? No, what is the failure rate? You need to read the problem description. It does say operating computer fails after exponentially distributed duration having mean time t sub f. So it's going to be 1 over t sub f. Is that right? Okay. Okay. So here, one thing I want to mention here is that you will not multiply by 2 here. Why? Even though there are 2 machines, so in the failed condition, because there is only one repair facility in this example, right? That's why you do not multiply by 2 here. Where is the eraser? Okay, this is the eraser. So you need to multiply by 1 because there is only one repair facility. Okay? So obviously here, there is only one failed machine. So the repair rate would be just 1 over TR. And then here, the failure rate is 1 over T sub F. Okay? Does that make sense to everyone? Okay. So now let's construct the balance equation that we talked about last time. So balance equation says that for each state, so there is a transition rate from each state should be equal to the transition rate into each state, right? So here, for state 0, transition rate from state 0 would be this, right? Only one. So I'd say that is lambda 0, 1, right? And this transition rate started from state number 0. So you need to multiply by pi 0 is equal to the transition rate into state 0, right? That is going to be only this, right? Which is lambda 1, 0. That is from state 1. So you need to multiply by pi 1. There is a balance equation for state 0. Is that right? So we need to do the same thing twice more for state number 1 and 2. So state, what is that? Sorry. State 1. Transition rate from state 1 would be this, right? Down here, and then up here, right? We have this 2. So that's going to be lambda 1, 0 plus lambda 1, 2 times pi 1, right? And then transition rate into state 1. One is from state 0, and then the other is from state number 2, right? So we're going to put that information. Lambda 0, 1 pi 0 plus lambda 2, 1 pi 2. Is that right? And then for state 2, that's going to be lambda 2, 1 pi 2 equals lambda 1, 2 pi 1. All right? Since this system of linear equations are linearly dependent, so we need to arbitrarily choose one. So I'm going to choose the second one and then delete it. But we have one more constraint, right? Pi 0, pi 1, pi 2 are equal to 1. So for this problem, let's suppose the average repair time is just 10% of the average time between failures. Okay? So let's just suppose the average failure time is, so average failure time is 10 minutes. And the average repair time is just 1 minute. Okay? So let's use this numerical value. Okay? So here, if you want to plug in that, so down here, okay. Instead of TF, we have 10 minutes. Okay? So let's have 10 minutes down here. But here we have 1 minute. Okay? This is 1 minute. This is 10 minutes. Okay? So let's use this value. So which means we have here we have 1, right? And then here we have 0.1, right? Which is 1 over 10, right? So likewise, down here, we have 0.1, and down here, we have 1, okay? Then what do we have from this first equation? We know that pi 1 is 10 pi 0. Is that right? And from here, what do we have? Pi 2 is 10 pi 1. So or we don't even need to do this, right? We can just simply use this. So down here, this can be rewritten as, instead of pi 0, we can put 0.1 pi 1, right? 0.1 pi 1 plus pi 1 plus, instead of pi 2, you can put 10 pi 1, right? So what is this? It's going to be 11.1 pi 1 is equal to 1. Is that right? So what do we have? Pi 1 is equal to 1 over 11.1. So from here, you know that? What is pi 0? Pi 0 is 0.1 times pi 1. So 0.1 over 11.1. So that is 1 over 111. Is that right? So what is this value? Something 0.00 something? What is that? What is 1 over 111? 0.009. Okay. So there is about 0.9%. Okay. So this is the answer for that question, right? We will say both computers will be simultaneously out of service 0.9% of the time. Is that right? Because pi 0, state number 0, indicates the number of computers in good conditions are 0. That means both computers are out of service simultaneously. Is that right? Okay. And since we talked about lambda, matrix lambda last time, let's practice. So why don't you build up matrix lambda based on this diagram? So instead of using the balance equation, we're going to use pi times lambda equal to 0. Okay? So let me redraw the transition diagram. 0, 1, 2. So we have 1, 1, and 1/10, 1/10. Is that right? So in that case, lambda matrix should be 3 by 3, right? So we have 0, 1, 2, 0, 1, 2, like that. So we have a transition from 0 to 1 with a transition rate of 1, right? So we have 1 up here, and there's nothing here. So on the diagonal, it should be -1, right? Starting from 1, we have 1, 2, and then 1, 0, which is 0.1. So on the diagonal, it's going to be -1.1. Is that right? Likewise, we have nothing, 0.1, so -0.1. Very easy, right? Now, using the formula pi times lambda matrix equal to 0, we're going to have pi 0, 1, 2 times lambda matrix, which is this. Okay? So from here, the first equation should be pi times the first column of this matrix lambda. So that's going to be negative pi 0 plus 0.1 pi 1 equals 0. Okay? Because this is 0. The second equation is pi times second column, right? So pi 0 minus 1.1 pi 1 plus 0.1 pi 2 equals 0. And then third equation is pi times last column of matrix lambda. So pi 1 minus 0.1 pi 2 equals 0. Of course, we're going to choose one of the equation, arbitrarily choose, and then remove it, right? And then also we're going to add summation of pi's, so equal to 1, because we are dealing with probability distribution. And it's very clearly seen that all of these equations are exactly same as the one what we considered earlier from the balance equation. Okay, so this is the alternative way to determine the steady state probability distribution. Also, in this case, you know that if we set, let's say, x of t is the number of computers in good condition in operating at a certain time t, then this x of t is also a birthday process. Why is that? Because in this case, the population, what is the population? That is the number of computers in good conditions. So always increase by 1, right? And then also decrease by 1. Is that right? And both, in this case, birth deaths, so independent each other. So obviously, this is the birth death process. Is that right? So that means we can use that streamlined formula. So let's also do that. So here, let me redraw the transition diagram. 0, 1, 2. Up here we have 1, 1. Down here we have 0.1. 0.1. Is that right? So what we have is 1 over pi 0 equals 1 plus 1. So you know we are using this formula now, okay? These two formulas. So here we're going to put the first rate 1 over first death rate 0.1, and then next term is the product of first two birth rate, which is 1, and then product of first two death rate, that is 0.1 square. Is that right? So what is this? That's going to be 1 plus 10 plus 100. Is that right? Which is 111. So what is pi 0? Pi 0 is 1 over 111. So I believe that's the same value that we got. Is that 0.009, right? Earlier. Is that correct? Right? So I just say it's about 0.9%. So we come up with the same result. See, this is a lot easier, right? To get the pi 0 value compared to, well, it's about the same in this case. Because it is very small size problem. But if you deal with larger size, of Markov chain model, then you're going to see that for the birth test process, using this streamlined version of formula is a lot easier to determine the steady-state probability distribution. Okay? So any questions so far? Okay, so if you don't have any questions, then let's consider in-class exercise problem. Okay? So everyone already got this, right? Okay. Okay. Okay, so let's read the problem description together. A local takeout Italian restaurant has space to accommodate at most 5 customers. So the maximum capacity of this restaurant, Italian restaurant, is 5 customers. So during the frigid winter, it is noticed that when customers arrive and the restaurant is full, virtually no one waits outside in the sub-freezing weather. Looks like they don't have any waiting room. Okay? But instead, they goes to next door to Pizza Hut restaurant. And customers arrive at the restaurant at the average rate of 10 per hour, according to a Poisson process. And the restaurant serves customers one at a time, first come, first served, in an average of 3 minutes each. And the actual timing exponentially distributed. Okay. And then the first question is, what is the steady state distribution of the number of customers in the restaurant? And then we have a couple more questions. So, okay, as usual, first let's define the state of system and then build up the Markov chain model. Okay. So let me give you maybe 2 minutes. Why don't you define the state of system and then build up your Markov chain model based on it. Okay, so how did you define the state of system? Yeah, sure. Number of customers in the restaurant, Italian restaurant. Okay. So let's start with the case with 0 customers. Okay, so I'm gonna put 0. Okay. So if there is no customers in the Italian restaurant, what is the arrival rate of the customer? it does say the arrival rate is 10 people per hour. Okay, so I'm going to put 10. Okay. Okay, then what is the service rate then? If there is one customer, what is the service rate? 3 minutes is a service time, but we need to put the service rate. So what number you're going to put it? What? We need to put the rate, not the time. 1/1. Not exactly, because you didn't consider the unit. We need to use the same unit, right? Either you're going to stick to minute or hour. Okay? So I would convert minute to hour first. What is 3 minutes? That's going to be 1/20 hour, right? So here, service rate would be what? It's going to be 20. Okay? Does that make sense? Okay. So if there is one customer already, then what is the arrival rate again? That's going to be the same, 10 per hour. And then we're going to have service rate all the way up to 5, right? And then the service rate is the same, because it does say they serve customers one at a time. First come, first service based. Okay? So you have 20 all the way. And what happened if there are 5 customers already in the restaurant? It's not going to be 10. It's going to be 0, right? Because of here, in that case, no one's going to wait, right? They were going to go to other restaurant, other pizza restaurant, right next door, right? So we don't have this anymore. Okay. This is this, okay? Like this. So this is our Markov chain model for this Italian restaurant problem. Okay? And here, is this burst test model? Right? Right. Because number of customers always increase by 1. Right? And then decrease by 1. Always. Right? And then customers arrival and service are independent each other. So obviously this is burst test process. Right? So in that case, we can use the streamlined version of the formula, which is 10/20, right? And then 10 square over 20 square, 10 cube, 20 cube, 10 to the 4th power, 20 to the 4th power, right? 10 to the 5th power, 20 to the 5th power. Very simple. Then what is this? So they are basically 1 over 2, right? This is 1 over 2. Okay, let me just write it down. This is 1 over 2 square, 1 over 2 cube, 1 over 2 to the 4th power, 1 over 2 to the 5th power. What is this? Is that 1 minus 1 over 2, 6 power 1 minus 1/2? Is that right? Maybe? I cannot remember exactly, but anyhow, could you, give me the value for this? What is this? I'm sorry? Point 1. Oh, I'm sorry. Yeah, 1.56. Oh, 96. 1.96. Okay, thank you. So let me rewrite down. So it's 1.96. So what is pi 0? So pi 0 is 1 over 1.96. So it's little over 50%, right? Is that, what is this? Could you give me the number? It's 0.5 something. That's right. 0.510. Okay, thank you. That is the approximate number. So here, how is that? Pi 1. Oh, I cannot use this. Okay. I have to use the next page. So what is pi 1? Pi 1 is this, right? 1/2 times pi 0. What is pi 2? Pi 2 is this, right? 1/4 times pi 0. What is pi 3? Pi 3 is this, times pi 0. 1/8 times pi 0. And then pi 4 is this, 1/16 times pi 0, which means pi 5 is this, 1/32 times pi 0. So you should be able to get individual pi values this way, right? That's very easy to do. Okay. So now you got part A, right? Okay. Now let's work on part B. Okay, so it asks you, what is the average number of customers in the Italian restaurant at any time? How do you get this? It asks you the average number of customers in this restaurant. How do you get it? Right, exactly. So let me just read through the diagram. So down here we have 0, 1, 2, 3, 4, and 5, right? We have 10, 10, 10, 10, 10, and then 20 each. Okay. Just ask you the number of customers in the restaurant at any time. So if you are in state number 0, how many customers are there? 0, right? So the average number of customers in this restaurant would be 0 times pi 0. Plus, if you are in state number 1, there are 1 customer, right? So 1 times pi 1. If you are in state 2, there are 2 customers. So 2 times pi 2. You have to do this all the way up to state number 5. 4 times pi 4. 5 times pi 5. Is that right? Make sense? Using the summation, it's going to be sum over I from 0 to 5, right? And then I times pi I. Is that right? And this is represented by L, capital L, okay? So does anybody already computed this value? Maybe you can do that at home. Because we didn't get this value, numerical value. So first of all, you need to do that, right? But those are very easy to do. So I'm going to leave this for you, okay? You can do this later at home. Okay, now let's move on to the next question, C. So what is the average arrival rate? Considering that when there are 5 customers in the restaurant, the arrival rate is 0. Of course, that is true. When there are 5 customers, the restaurant is full. So the arrival rate is not 10. It's going to be 0, right? Because all of them, whoever intended to come originally, they're going to move to the next restaurant, pizza restaurant. So the arrival rate, when there are 5 customers, should be 0, okay? And if you are in state 0, what is the arrival rate? 10, right? If you are in state 1, again, it's 10. 2 is 10. Is that right? So just like we did in the earlier, what you need is 10 times pi 0, 10 times pi 1, 10 times pi 2, 10 times pi 3. 10 times pi 4, 10 times pi 5. No, the last one should be 0, right? Here, 0 times pi 5. Is that correct? So here, I decide these values are equal to lambda bar. That is the average arrival rate, Okay? So keep in mind that in the burst test process, more in general, the queuing theory, the average arrival rate is represented by lambda bar. And the average number of customers in the system, and the entire system is represented by L. Okay? Then, here's the next question. Next question asks you the expected amount of time the customer spends in the restaurant. So it's been asking you average waiting time in the entire system, okay? In the burst test process. And in general, in the queuing theory, it is represented by capital W, okay? And I gotta tell you that there is a very famous theorem which is called Litter's law. According to the Litter's law, L is equal to lambda bar times W. Okay? So using the Litter's law, we can compute W. What is W? That's going to be L over lambda bar. We already got L from part B, right? And then lambda bar is from part C. So you should be able to get W, which is the expected amount of time your customer spends in the restaurant. Okay, now let's move on to the last question. So it asks you, what is the fraction of potential customers who are lost to the pizza establishment? So how do you answer this question? So what fraction of potential customers lost to the pizza establishment? Do you remember? If there are 5 customers, you're going to lose every customer, right, to the pizza restaurant because they decide to go there instead of coming in to your restaurant. Is that right? So what is the answer for that? Five. Very simple question. Is that? Okay, then what is the following question? What is the number of customers per hour lost to the pizza establishment?
5. 5 minus 5.
Can you speak up?
You said 5. You said like the rate is 10 dirham or so.
Right.
The capacity is 5 already.
Right.
Okay, so they're gonna lose the other 5 since the capacity is.
Not exactly. So this amount, okay, this fraction of customers will go to the pizza restaurant, right? And then down here, it asks you the exact number of customers per hour lost. So what you need is pi 5 times what? 10. Does that make sense? Okay. Actually, this is 10 per hour. So your answer should be some value, right? Per hour. Does that make sense? Okay. Okay, so these are for today. So next time, I'm going to give you another set of exercise problems for the continuous time Markov chain. Okay? And let me know in the meantime if you have any questions regarding my lecture materials. Okay, thank you. Bye-bye.